So welcome to today radar systems class. In today's class, I recall all the important concepts in second unit, and as well as the concept of multiple frequency CW radar, which is the last topic in your second unit. Okay. So first we'll see the syllabus in your second unit. What are the topics we already discussed in this second unit? So see here. In the second unit, you learned already about continuous wave and frequency modulated radar, right? So in this unit, all the types of radar are based on the effect called Doppler effect, right? So first we'll see what do you mean by Doppler effect. Basically, what are the types of radar systems now? Basically, radar systems are classified into two types, right? First one is continuous wave radar, second one is a pulse radar. So, if you transmit continuous wave as an electromagnetic wave towards the target, then such type of radars are called as continuous wave radars, right? Okay. So if you transmit pulse as an electromagnetic signal towards the target, if you means here radar system, if the radar system transmits continuous wave as an electromagnetic wave towards the target, then such type of radar is called as continuous wave radar. Or if our radar system transmits pulse as an electromagnetic beam towards the radar system, towards the target, then such type of radars are called as pulsed radars. Okay. In continuous wave radars, we have two types. First one is unmodulated continuous wave radar or Doppler radar. Okay, right? Whereas coming to pulse radar, in a pulse radar also we have two types. First one is basic pulse radar, which is used to measure only stationary targets. Whereas coming to continuous wave radars, both unmodulated continuous wave radar, frequency modulated continuous wave radar, both are used to detect non-stationary targets. Both types of continuous wave unmodulated Doppler radar or continuous wave frequency modulated radar, both types of radars are used to detect moving targets, right? I recall all the concepts. Please try to concentrate. I'll give tip points, right? So whereas coming to pulse radars, we have two types: basic pulse radar, moving target indication radar. Where basic pulse radar, in this pulse radar, the transmitting electromagnetic wave is a pulse wave, right? So this basic pulse radar is used to identify the only stationary targets, not moving targets. Okay. So what is the next type in that pulse radar? Moving target indication radar. So as the name itself explains us, it is used to detect the moving targets, right? That is your third unit. Second type of pulse radar is your third unit, right? So in your second unit, you learned about continuous wave radar, continuous wave frequency modulated radar, continuous wave radar with the non-zero IF receiver. All these topics already you learned. Okay. So all these topics are based on the concept called Doppler effect, right? So what do you mean by Doppler effect? So whenever an electromagnetic wave touches the moving target, what do you mean by a Doppler effect? Whenever an electromagnetic, in terms of radar terminology, or in terms of general, whenever a wave touches the moving object, definitely there may be a shift in frequency of the transmitted wave with respect to the moving target. That is, the shift is called as, the frequency shift is called as Doppler shift, and that phenomena is called as Doppler effect, right? So see now here, in terms of radar terminology, so whenever an electromagnetic wave hits the target, definitely frequency of the transmitted electromagnetic signal shifts when compared with the transmitted frequency. The shift is called as Doppler shift, and the phenomena is called as Doppler effect. The change in that frequency is used to analyze the range and used to detect the target, moving target, right? So you already did, you already learned about continuous wave radar, which is unmodulated one, which is used to measure a moving target. Here it is with zero IF. Initially we discussed about with zero IF, no intermediate frequency is introduced in this session, and we analyze the drawbacks of this continuous wave radar, which is also called as continuous wave Doppler radar. What are the main drawbacks in this one? Flicker noise is introduced, and isolation due to lack of isolation between the transmitter and receiver. There may be a chance of receiver burnout, and there may be so many problems, right? So, and third one is it is not able to measure the range. It is only able to detect the moving target, but the range measurements are not possible with the basic continuous wave unmodulated radar, which is also called as the continuous wave Doppler radar, right? So, Seema, so after analyzing this continuous wave radar, we have mainly three disadvantages. First one is flicker noise, where flicker noise is having a force factor density of 1 by f, right? So that means flicker noise is proportional to 1 by f, means if you increase the frequency of operation, then automatically the flicker noise will decrease, right? So in order to decrease the flicker noise, we need to use some higher frequencies rather than the frequencies what we are used in this continuous wave radar, right? So Seema, so for that purpose, we are moving to the other concept called continuous wave Doppler radar with non-zero IF receiver. Okay, and in this continuous wave Doppler radar, we are using duplexer as an antenna. That means there is no separate antennas for transmitting and receiving purposes, right? We are using a single antenna for transmitting and receiving purposes. So that creates isolation problem. There is no isolation between the transmitter and receiver. So no isolation means actually the transmitter power is in high range, that is in megawatts range, but the received echo signal power is in watts range. Okay. So whenever you design a receiver circuit to operate with a power range of watts and milliwatts, but if the transmitter leaks megawatt power into the receiver station, then there may be a chance to burn out the receiver station, right? So in order to avoid that, in order to provide an isolation between the transmitter and receiver, in continuous wave radar with non-zero IF receiver station, we are using two separate antennas for the purpose of transmitting and receiving, right? So in this one only, we already analyzed the bandwidth requirements, receiver bandwidth, all the things, okay? And several applications of a continuous wave radar and the problems, okay? So problems most probably based on the Doppler effect concept, right? See, all these topics we already I already discussed, and you learned all these topics, right? So Seema here. So where is the first design? A continuous wave radar, basic continuous wave Doppler radar. We analyze the drawbacks, right? We avoid two drawbacks which is noticed in basic continuous wave Doppler radar. First one is the flicker noise, and second one is isolation by using continuous wave Doppler radar with non-zero IF receiver. But even though by using these two methods in non-zero IF, continuous wave Doppler radar with non-zero IF receiver, there may be another disadvantage, that is the range is not able to detected by continuous wave Doppler radar, but the moving target is only detected. Okay, range is not calculated. So in order to calculate range of the continuous wave Doppler radar, we are going to the concept called FMCW radar, frequency modulated continuous wave radar, second type of continuous wave radar. In a continuous wave radar, which have a two types. First one is continuous wave unmodulated radar, which is also called as continuous wave Doppler radar, and another one is a frequency modulated continuous wave radar. So from the basic continuous wave Doppler radar, we are moving to the continuous wave Doppler radar with non-zero IF receiver, right? So with non-zero IF receiver, right? With this, you avoided two drawbacks, which was introduced in a basic black diagram, basic continuous wave Doppler radar. That is flicker noise and an isolation between the transmitter and receiver, right? But the third drawback is not avoided in this one also. That is calculation of range. That was possible by using design of frequency modulated continuous wave radar. Okay, so in this frequency modulated continuous wave radar, I already explained about range and Doppler measurements. How you are going to, what is the main advantage of this FMCW radar? Range calculation, because it is not possible by using a continuous wave Doppler radar, right? So the concentration in this FMCW radar is, main concentration is how we are going to calculate the range when compared with this continuous wave Doppler radar, basic continuous wave Doppler radar, right? And how we are taking a Doppler measurement, black diagram, characteristics, right? That that is we already discussed. And next concept is FMCW Altimeter. Altimeter is an application. Okay, it is an application of FMCW radar. Okay, and I think last class we already discussed how FMCW altimeter is working and how it provides above AGL measurements. AGL is nothing but here above ground level measurements. Okay, it gives an altitude of aircraft from the ground level, right? So in your second unit, the last topic is multiple frequency CW radar. Okay, so in today's class, I will explain about multiple frequency CW radar. I think my voice is audible. If any problem, please let me know. Okay, so this is multiple frequency CW radar. Okay, so I will show. I will explain that multiple frequency CW radar. So with this, your second unit is completed by today class, right? So Seema, before that, I want to show the image. Here, see this image. This is the first generation radar. Actually, uh, the radar which is used to detect, not detecting, that means it gives some intimation to the radar operators about the flying object. That means it is only detects the object. It doesn't give any calculations, accuracy measurements recording that target. Okay, how size, observe the size of this radar, right? But now this is the early generation radars which are only limited to military applications. See? But now, what is the radar size? How miniaturized is the radar size? They come to incorporated in a police radar guns, right? And they are also used in fuses. What is the size of fuse when compared to this size? What is the size of fuse in fuses? Proximity fuses also we are incorporating. We are integrating these radars, right? See, what is the size of this fuse? In this fuse also we are integrate. We are placing our radar to detonate a bomb, right? So how much is try to understand how much huge research is going on towards the radar system. Okay, from the early radar systems to today radar systems, right? So in your second unit, you have only the concept called multiple frequency continuous wave radar. Okay, I will explain the concept clearly. Try to concentrate on that concept. See here. So this is about the FMCW radar. So Seema, here your last topic in your second unit is multiple frequency CW radar. So when you going to learn about the concept of this multiple frequency CW radar, it's a very simple concept. Actually, what is I just now explained what is the drawback of basic continuous wave Doppler radar. What is drawback, ma? Main drawback is it is not able to calculate the range when that range is going to be calculated by a frequency modulated continuous wave radar. It only the basic continuous wave Doppler radar only detects the target, right? It doesn't give any change information, right? So there may be a possibility of measuring the continuous wave of measuring range using continuous wave Doppler radar, right? That possibility is accomplished by using the multiple frequency continuous wave radar, right? Here the concept is very simple. Please try to concentrate. Concept is nothing but actually what is the drawback of basic continuous wave radar? Drawback is it doesn't give any information regarding range, right? But in some situations, we may able to calculate the range by doing some modifications. Okay, that modified design of actually the multiple frequency continuous wave radar is design is same as like the basic continuous wave Doppler radar, but the principle of operation and the way of measurement is different, right? So that modified design of that basic continuous wave Doppler radar is also called as multiple frequency continuous wave radar. I will explain next what is that modification, how we are able to measure the range by using a basic continuous wave Doppler radar, right? So actually, so before going to explain all these concepts and before going to derive the equations for this multiple frequency continuous wave radar, I told one concept. I will told one concept here, that is actually the radar transmitting antenna transmits one pulse towards the target, right? Actually, for detecting a one target, radar system transmits one not echo pulse, one electromagnetic pulse towards the target, right? But instead of transmitting a one pulse, compare it with an integration of radar pulses. While analyzing the target information, while while performing calculation of parameters related to target, you are considering n number of echo pulses into an account, and those n number of pulses are integrated. That concept is called as integration of radar pulses, right? Similarly, here, instead of transmitting a single continuous wave, you are transmitting two or more continuous waves, right? You are transmitting two or more continuous waves towards the target, and you identify the phase difference between those two signals in order to measure the range of the target, right? So with this technique, it is possible to measure range of the target by using a basic continuous wave Doppler radar, right? Simple concept. Instead of transmitting a single continuous wave, you are transmitting two or more signals. Assume like that. And you are identifying the phase difference here. You are using the phase information to calculate the range. I will explain how we are calculating the range by using that phase difference. So no need to worry. But here the thing is, what is the thing here? You need to calculate the phase difference. Okay. So the phase difference is used to calculate the range of the target, right? So Seema here, a continuous wave radar cannot measure the range, right? That was the drawback of basic continuous wave Doppler radar. But it is possible by measuring the phase of the echo signal relative to the phase of the transmitted signal. Okay. But we can able to calculate the range by doing like this. What we are doing here? Radar system transmits an electromagnetic wave towards the target, right? That is having one phase. Okay. and returned echo signal is having another phase. Here we are using the phase difference in between the transmitted signal and the returned echo signal. So by using that phase difference information, we are calculating the range of the target. That's why it is possible by using multiple frequency continuous wave radar. We know basically in our integrator differentiator concepts only, in our analog communications only. We know that one thing, frequency and phase modulations are called as angle modulations. Both the modulations are called as angle modulations. Why they are called as an angle modulation? When you change the frequency and phase of the signal, angle of the signal is varies. So that's why those are called as an angle modulation, right? So that means here, actually, if you change the frequency, these two are interrelated. Phase of the signal also changes, right? So by using the phase difference between the signals, you are going to calculate the range. Don't confuse by seeing all these points. Only the concept here is you are comparing the phase difference between the transmitted signal and a received echo signal. By using that phase difference, you are going to calculate the range of the target by using an FMCW, not FM, basic CWR radar. That concept is called as multiple frequency continuous wave radar. Why you are called that as a multiple frequency means here instead of transmitting a single continuous wave towards the target, you may transmit two waves, two continuous waves, right? I will explain that concept later in these points, right? So here the phase of the transmitter, by using the phase difference between the two signals, that is transmitted signal and echo signal, we are able to calculate the range of the signal, right? So consider a continuous wave radar radiating a single frequency that is represented as sine 2 pi f naught t. If you consider a continuous wave radar and that is transmitting the frequency of sine 2 pi f naught t, right? And the signal reaches the target, right? Seema, observe here the concept. Now the signal hits the target and that signal returned back to the radar system. The signal is returned back to the radar system as an echo signal. So here we are analyzing the time. Sorry for the interruption. Here we are analyzing the time required. Here we are analyzing the time required for the echo signal to reach the radar system again. Okay, so see, the time is t is equals to 2r by c. We know that this equation where range r is equals to ct by 2. From that we are deriving the time t is equals to 2r by c, right? If the transmitted and received signals are compared in a phase detector, so in addition to a basic continuous wave Doppler block diagram, we are using an additional block called phase detector. Remaining all the blocks are same as like basic continuous wave Doppler radar, right? So here by using this phase detector, the phase of the transmitted signal and received echo signals are compared, and that phase difference is given for the measurement of the range. Now we will see how we are measuring that range by using the phase difference, right? So I think here you got the concept. Basically, this multiple frequency continuous wave radar is used to measure the range of a target by using the phase difference. Which phase difference? Between the transmitted signal and the received echo signal, phase difference is calculated. That phase difference is used to measure the range of the target. Why we are calling that as a multiple frequency continuous wave radar means we are using more than one continuous wave. Okay. So see here, actually the transmitted signal phase and the received echo signal phase is given to a phase detector. Now the output given by the phase detector, which will compare with the transmitted signal and the received signal, is written as that phase difference is given as del phi where del phi is equal to, we know that 2 pi ft, right? Now del phi is equal to 2 pi f into t. T is nothing but time taken by an echo signal to reach the radar system from the target, right? So the time taken is given here 2r by t. So it becomes 4 pi f(r) by tr. So from this you can write range r is equals to del phi is equals to this equation. Bring r is equals to c del phi by del phi is equals to, again it is c del phi by 4 pi fr. So if you bring r is equals to, it becomes we are expressing Cf in the terms of lambda, so it becomes lambda del phi by 4 pi. Simple calculations, substitute, do it on paper, you'll get this answer, right? Lambda del phi by 4 pi. Now I think now you are clear where range r is equals to, put here range r is equals to lambda into del phi by 4 pi. What I already told, that by using the phase difference information, we are able to calculate the range of the target, right? It is proven here, right? So by using r is equals to del lambda into del phi by 4 pi by 4 pi. But here we have some limit. If this del phi is equals to 2 pi, there is a large ambiguity present regarding the target. So always this phase difference, we must keep this phase difference less than 2 pi, okay? So if you substitute del phi as 2 pi, then what it becomes, r is equals to lambda by 2. In that case, maximum ambiguity is present regarding the target location detection, right? And I already told that block diagram is as similar to basic continuous wave Doppler radar. In addition to that block diagram, in a receiver section, only the phase detector block and channel is included, right? So the transmitted waveform is assumed to consist two continuous sine waves of frequency f1 and f2. Here I already mentioned that instead of transmitting a single frequency, single continuous wave frequencies, we are transmitting more than one continuous wave frequencies. That is denoted here, f1 and f2, separated by an amount of phase difference del f or frequency difference. This is del f means frequency difference. Okay. So now those signals are represented as V1R and V2R. Those are represented as V1R is equals to sine of 2 pi f1t plus phi 1, and V2R is equals to sine 2 pi f2t plus phi 2, where phi 1 is phase of first signal, phi 2 is phase of second signal. But here the concept is, by analyzing the phase difference between these two signals, phi 1 minus phi 2, that is represented like here del phi. So by considering that the del phi into an account, we are able to calculate the range. That's the concept here. So these are the signals. Okay. So where phi 1 and phi 2 are the arbitrary phase angles. This is the normal representation of a signal. We know that signal V1 is equals to sine 2 pi ft plus phi, right? Here we are considering the two signals. That's why we are representing these as sine 2 pi f1t plus phi 1, sine 2 pi f2t plus phi 2. Right? These are the transmitted signals, right? Initially, till now we discussed in all the cases, we are transmitting a single pulse towards a single target, right? But here we are transmitting two pulses which are having two frequencies, f1 and f2, and the frequency difference is here del f. Whenever there is a frequency difference in between the two signals, there should obviously there is a phase difference also, right? So the echo signal is shifted in frequency by the Doppler shifter, and here these are also used to detect the moving targets, right? So whenever these are used to detect the moving targets, whenever these signals hit the moving target, obviously there is a shift in frequency called Doppler shift. So see here the Doppler shift is indicated here. So see this derivation here, that is represented the Doppler shift is Doppler effect, and the form of the Doppler shifted signals corresponding to the two frequencies f1 and f2 are given as v1r is equal to sin 2 pi f1 plus t means time information is given here f1. The Doppler shift is represented as plus or minus fd1. This is the time information, minus 4 pi f1 r naught by c plus pi 1. V2 or in a similar manner, V2 or is equal to sine of 2 pi f2 plus or minus fd2 into t minus 4 pi f2 r naught by c plus pi 2. Simple, here we are representing the Doppler shift concept, right? The plus or minus fd1. This one is the response of information of time. Okay, time response time, and this is the phases phi 1 and phi 2. So here see, R naught is range to a target at a particular time t is equal to t naught. Range that would be measured if target were not moving. Okay, and FD1 is if the target, if you consider target as a moving target, definitely there may be a Doppler shift. So that is indicated here. FD1 is Doppler frequency shift associated with frequency f1, and FD2 is the Doppler frequency shift associated with the frequency f2. Since the two RF frequencies f1 and f2 are approximately the same, then f2 is equal to f1 plus LF. Okay, these are the several conditions to calculate the range of the target. On whole, here the concept is very simple. That is, first thing, see here, what is the name of this concept? Multiple frequency CW radar. Okay. Why we are using this concept means, if you question why the discussion, why we need to include this topic in our radar systems means, the drawback of basic continuous wave Doppler radar is it is not able to provide the range information of the target, right? So in order to provide the range information, we are moving to the concept called frequency modulated continuous wave radar. We already discussed that concept, right? But instead of that, you can also be able to measure the range of the target by using a basic continuous wave Doppler radar design by doing some modifications. Here, what are those modifications? Here, range is calculated by using phase difference information, right? And why we are called that as a multiple frequency means, here instead of transmitting a single continuous wave, we are transmitting more than one continuous wave frequencies at different frequencies. So that's why it is called as a multiple frequency. Okay, so we are observing, we are transmitting at multiple frequencies, and we are observing the phase difference between those two frequencies, those multiple frequencies, and by using that phase difference, you can able to calculate the range. And this equation explains you how you are able to calculate range by using the phase difference, by using del phi, where del phi is nothing but phase difference between the two signals, right? I think now you got the concept.